we're all human and we know what it takes to be a human, but still we struggle to bake this into our computational models for reconstruction or synthesis or for driving our robots and so on. We have made a lot of progress as a community, but still we meet new challenges. For example, for social interactions, human-human interaction, either between two persons or in a crowd. We also interact with objects and scenes, and this poses a lot of challenges and ambiguities. We have a lot of strong occlusions. The body occludes the object occludes the body. We have the body and the hands operating at very different scales, and this poses challenges. For example, for fingers, we have fine-grained motions. We need to tackle allocentric third-party views, but also egocentric views nowadays with the mixed reality headsets. And we also don't operate in isolation. We operate within our 3D world and 3D environments. So hopefully today we will cover a lot of ground for tackling these challenges. We have an exciting lineup of speakers. First, we have Anju from UC Berkeley. Then we have Michael Black from the Max Planck Institute for Intelligent Systems, Gerard Pons-Moll from the University of Tübingen, Sebastian Starke from Meta, and Han-Bol Ju from Seoul National University. Shout out for the organizing team. The people in the first row did the bulk of the job, so thank you everyone. We have Qianli Ma from NVIDIA, Siwei Zhang from ETH Zurich, Shashank Tripathi from MPI Tübingen, Raval Kidrokar from Meta, Yan Zhang from Meshlapade, and Yao Feng from Stanford. We don't have enough gray here, but at the bottom row, we have the Senior Advising Committee with Georgios Pavlakos from UT Austin and Siyu Tang from ETH, and myself from the University of Amsterdam. We'd like this workshop to be fun, so we do encourage questions. During the talk, please note down your questions. So at the end, we will have a Q&A session. So we encourage everyone to walk to the microphone, and let's keep it interactive and fun. And for people that attend remotely, please type your question anytime in Zoom chat, and then we will take care of this. This will be the schedule for today. First, we have Anju, then we have Michael, who will talk about humans in motion and contact for 3D behavior understanding. Then it will be Gerard Pons-Moll, who will talk about training large-scale models for reconstructing human objects, scenes, and bodies. Sebastian Starke, who will talk about neural animation controllers, and Han-Bol Ju, who will talk about generative models and exploiting these for 3D human object interactions. At the end, George will hold a panel discussion with all of our speakers. Hopefully, this will be a nice workshop, so hopefully you will want to remember this for the years to come. So we have some souvenirs. During the poster session and before the beginning of the second session, please come here at this desk, and we have some souvenirs for you. Without further ado, let's welcome Anju for the first talk.
Hello.
So while we set up, let me introduce Anju. Anju is an assistant professor at UC Berkeley, where she leads the Kanazawa AI Research Group as part of BEAR. Anju has been named a 2023 Sloan Research Fellow, and she has received the PAMI Young Research Award in 2024. Her work focuses on building systems that perceive our dynamic 3D world, including people, animals, and humanoids, as well as their interactions, from several modalities, for example, from everyday images and videos. And without further ado, the stage is yours.
Thank you so much for the nice introduction. Okay, all right, let's get started. So today my talk is about how to train your humanoid. So basically the path from HMR to video mimic. Okay, so I've been working on this problem for a while. This paper is almost 10 years old now. And so this is what the results used to look like. And this is the result that used to look like in 2019 when we did the human misrecovery, which is the first feed-forward method, or one of the first feed-forward method. Of course, we've been working on making this better and better with HMR 2.0, and George really pushed on this direction for understanding hands. And now we can do all of these things, we can understand these Italian hand gestures. Okay, so really, what's the end game here? And I think a lot of the my most inspiration has been this video, learning to act from video. And in this one, it's such a great video because this baby is clearly watching the TV and imitating the motion and the TV and understanding the 3D motion that is happening behind it. Okay, so this is one of the goals that I've been working for a while. And then, what we really want is, we want to build robots that can do the same thing as humans, in wherever that can do the same thing as people can, wherever people can, So we don't need to restructure our homes to accommodate these robots, but we want the robots to have the same form and navigate the spaces like we do and do anything that we can do. And so apparently it is the summer of humanoids. There are actually a lot of hardware platforms that are available for much more reasonable prices. And even there's, and then so it's really starting to be accessible. There's a lot of developments in advance in control. Now we kind of know how to do deep learning with control. So we can do these type of things with imitation or RL. And these have kind of started to go to the legged domain to how to actually control the whole body to achieve these complex tasks. But currently, existing approaches are mostly, now they can do multiple things like track any references, but there is no scene. And when there is a scene, when it's non-flat, it's often designed by hand. And this is not bad. You can go up on the simulated staircases, but there's many different kinds of staircases. And so what do we need? What do we need? What is the thing that we need in order to... Data! Yes, very good! Data! And what kind of data? The video is best because it has both people and the environment. And so this is something that we've been working on for a while. This is a SIGGRAPH 2018 paper called Scale from Video, where we are, doing this thing. And this was one of the first ones to take videos, YouTube videos, and learn to act in the policy. So, okay, so here's some results from that time. So let's just focus on the videos on the left. And actually, can you notice something about these videos? I had to specifically look for YouTube for certain types of videos. Do you have any guesses? No scene. Yes, there's no scene. Actually, there is one scene that Jason, the first author, actually made by hand. Okay, but another thing. Static camera. Okay, yes. Okay, so the camera is not moving in flat floors only. And so this is because we focused a lot on reconstructing the human body pose. But then we do it in this bounding box and we have nothing, we don't have any information actually about the distances between these two people or how fast that they are running in the world. And this turns out to be the most important information when you go to simulation, because this is the first order information. In order to figure out how much force to put in, you really need to know how much displacement you would like to have. And this is none of that information. And this is actually a really challenging problem because if you look at this video, the person is clearly running through this field, but if you notice, the person is always at the center of the video scene, okay? And this is because the camera is tracking this person. So whatever we see in the video is a combination of human motion and the camera motion. It's really impressive how, I think the camera is actually one of the biggest bottlenecks, and we've seen such big advancements recently. But it's really cool that when we are looking at this video, you're essentially factoring away the camera motion. But this is really quite a hard inverse problem, right? This is like A plus B is equal to C. So what is the A and the B? If you don't count for that camera motion, you're going to get these results where the person is running in place because you're not explaining it. But then if you actually use SLAM or Visual SLAM to get the camera, then you can actually start placing people in the world with their global translation. So this was one of the big message in this work called Slummer, and it was exciting because this is a slide that I always use to start my talk. And then with Vicky, we came quite far in reconstructing the scene. And for this, this is also really cool because we were using some kind of floor constraints, which gave us different height differences. And we're explaining the camera, as you can see. So at this CVPR, we took this idea further, but Slummer is actually a really, really hard problem. I don't think we've really solved it yet. So we went back one step and we went with the multi-view images, okay, with known identities as an input. So this is a work presented at CVPR led by Leah and Hong Suk. And so the input is multiple view images, thanks for data sets like Eagle 4D, and you know who they are, okay? So the association is done. And the output that we're getting is this reconstructed the scene together with the 3D point maps and the camera poses and the 3D human meshes. And so we're really taking on a lot of advancements from methods like Duster that is able to give us really nice point clouds and cameras. But naively putting together the latest HMR and then Duster will result in this type of floating scene where it's not really coherent and the scene is also not that best. But after HSF optimization, the people are in the correct places and the scene also looks better. Everything is being updated. And so the most exciting thing about this work, this is really thanks to the multi-view aspect too, but that we were really able to see the synergy in the joint optimization. So of course, places and cameras are like one side of the same coin. This is structure for motion. But the camera help place people. Like because of the camera motion, you get to actually recover their global motion. But the places actually allow you to also see what kind of things that humans are interacting with. But in this work, we also showed that the human scale, the idea, like the models are actually metric scales. And so the scale kind of allows you to resolve for that ambiguity, scale ambiguity in SFM, and also bring in correspondences. And it actually helps. This is the most exciting result. This is reconstruction of the gym, and the gym is supposed to be rectangular with like 90-degree angles. Okay, it's not perfect, but the previous one is the results of Duster. And after you incorporating humans, you see that humans are in the proper places, and the scene actually looks better. So this is like the cool synergy that like we think that the humans are also useful to understand the images, and that's kind of happening. The approach is essentially an optimization-based approach. We take a lot of the state-of-the-art, key point detector, HSFM, and HMR and Duster-like approaches, and then we solve a big bundle adjustment. Maybe without getting into the details, perhaps the most important part is to resolve the scale ambiguity of a scene. As you know, if you run reconstructions multiple times, you'll just come up with different scales. This is actually quite non-trivial because if this can be from like 0.0 something to like a very big number. And so if you arbitrarily start your optimization, your people might be behind the cameras, and then you can't actually optimize this. And this is actually quite tricky. We tried a couple of methods, but the one that worked the best is also the similar type of initialization that we've been doing in all of these works, but to use this type of similar triangle relationship to identify a camera in each scene. Okay, so for each scene, we pick one person, and we basically align that person to every other person. Now this gives us a human-centered camera, i.e. the camera that is being predicted by the HMR method, like the orientation. And once you have this, and then you also have a Duster camera, then you can actually align them using Procrustes, and then that's kind of how we do the initialization. And this is kind of important because otherwise, if they're not in the scene, it can be degenerate. Okay, so after doing this alignment, which allows you to get reasonable scale for the world, they're still not really in the right place. And so in this part, we do this joint optimization where we change the scale of the world as well as the locations of the people and do global alignment. This is like the bundle adjustment in Duster. So we do simplify and Duster together. One thing is that because this is multi-view, we don't use any contact constraints. And so that's kind of nice that, it's like contact is good and bad. That like, if you don't have to it's nice to actually not have to do it, and the multi-view nature really helps you. Of course, you have to have reasonable number of views. But 4 or 3 is what we are working with. Okay, so now after that, everything looks reasonable. Just to kind of go on the numbers, like the number is better with the joint optimization in the world. The exciting thing here is that Duster and Master are quite competitive baselines, and doing human optimization does improve on top of them, which is exciting to see. Okay, so the nice thing is, once you actually have this reconstruction, you can answer these questions like from this image, like who jumped higher? So here's some reconstruction in Visor where you can actually see that the David is slightly taller, slightly jumping faster, taller. And then you can ask questions like, is Tyler closer to Arthur or David? And my students implemented Visor is this visualization tool that we use, and my students implemented ruler in it, so you can like grab a point and you can actually get the distance in meters, because now the world is actually metric. I mean, of course it's going to be off, but it's an estimate, right? But this is actual meaning. Okay, so that was cool. And after we got that, we were like, okay, so now how do we take it to monocular video? So given a single video, we wanted to reconstruct both the scene and the human motion. And we did this, and I will describe how we are going to do this. But with this, we were able to do this project. Let's see. Yeah, so this project we called Video Mimic. So this was one of the first, I think this is the first time humanoid was walking around campus in the wild across all kinds of terrain. It was a really fun day to film because like people were like, oh my God, it's kind of interesting what they do. And so this is a really big work led by 4 co-authors, because this is a really big project. Arthur Hong-Sak, David Jui, with Anthony and CMK's help, and professors. Okay, so the title of the paper is Visual Imitation Enables Contextual Humanoid Control. And so I think one interesting thing about this paper, this work, is it's not just that we actually did the real humanoid demo. It's actually, I think it's really adds an interesting aspect to how we really should have these robot controllers. So the thing is, these robots is given a route direction, which direction to go. But it's a contextual control. We call it a contextual control policy because we don't really tell it what kind of motions to do. So it's really depend on the environment. If you go back, and if there's something to sit on, it will sit. And so this is one continuous take where now we're like, okay, go forward, and it actually goes up the staircase. It's for one of the first time it's walking in the world. And then now it learns to come back. So the inputs that this robot has is a LiDAR height map, like 11 by 11. And it all decides how to walk up, down, and sit. And I will describe that. I'll explain this more, but the current controller for humanoids often require like what joints to do, and this is not a bad thing. You might want the humanoid to like do a specific thing and shadow you. But the thing is, when you're actually trying to walk up a staircase, it's actually unclear what should the command be. I mean, unless you're shadowing, then you're walking up the same staircase. And what if you don't have the staircase? And so this is why when it comes to incorporating the context, you actually have to make the robot decide what to do. And so to enable this, we train our policy on like 123 human video demonstrations that were collected on campus and throughout the places on Berkeley. And here are some of the reconstructions shown from different views. And this framework also works for 2 people, as long as up to sum 2, as long as we can actually track multiple people, reconstruct multiple people in the scene. Okay, and so the basic idea is reconstruct it and then take the scene and train in the simulator. But there's actually a lot of nuances to make this work, and so this was a lot of work to do. So the input is monocular video. And in trying to do the reconstruction, we have to keep in mind that we want to do this in the world coordinate frame so that we get this distance in the world. You actually also then have to convert these scenes, which are all point clouds, actually, dense point clouds. That looks pretty good to us, but you can't use it directly in the simulator. So you have to convert it into a mesh format, and then resolve the embodiment gap. So that's like one big idea. In detail, how this works is that we get all of these predicted off-the-shelf methods. So thanks to all the works, we use Tram for humans, Bistro for contact, VIT pose for key points, and Megasam for the camera and the point cloud. Then we do this reconstruction. And the reconstruction is very similar to HSFM, except it's only one view. So really the difference is that, okay, we do the align scale, which is the same thing that I just talked about. And then we optimize the human shape, location, pose, the world scale, and the smoothness. The major difference here is that we're guiding the human global 3D location by the predicted human point maps in Megasam or Duster or like a Monster or Aligner, all of these approaches. So because we're not using any human motion prior like we did in Slummer, I think it would be a really good thing to incorporate in this one, because now we're really relying on the quality of these Megasam-like type predictions, which is trained on synthetic data like Bedlam or like all of these other things. So it's not, I think there's a lot more work to be done here. That's how we initialize and we smooth it out. But surprisingly, it actually works reasonably well. So this is like some of the point cloud reconstructions and the reconstructions. Okay, so now we actually have the reconstruction in the simple world. Also, I'm happy to take questions, actually. I should have said this in the beginning, but hopefully, okay. And then now we have to do kinematic retargeting. So what does that mean? Okay, the number, so it's important that when you do these things, the number of the bones and the joints in the humanoid is not the same as the simple. So first thing we do is optimize the human beta to have the similar joint proportions to G1. G1 is like a kid height. It's like this height, this tall. And then we incorporate the contact constraints and retargeting, solve for the IK, do the solve for the joint angles of this new robot so that it actually matches. And we use this Pyroki, which is a new like a PyTorch for all of these robot kinematic tasks. I have more slides on it later. We meshify the scene with a neural kernel surface reconstruction method, which is a really nice generalizable method. And then we estimate gravity with geocalibration on the first frame. We align everything to it because we have to do it. Okay, so now finally we have this simulation ready data. And we don't actually use this information yet in this work, but the cool thing is that this allows this type of RGB rendering pretty quickly. And so that if you wanted to train your robots with it, this type of framework also allows that. Okay, so, but perception is not the end of the story, because once you actually perceive the 3D pose, you also need to actuate your muscles to get to the pose. It's actually a little bit nuanced, because in these ones, the action state is actually the joint angles and the PD controller is the one that is doing the torques. But regardless, you still have to go from this type of like just perceived kinematic motion, which doesn't have any dynamics, which is the joint angles that's not really physics compatible. And you actually need actions that are compatible with the physics of the world and the robot. And so this one, you do it with reinforcement learning. The objective of the reinforcement learning is that you have the reference in the robot, and there's a difference in the error of the joint and the states. You want to just minimize this error, and that is your reward. Actually, in the paper, we have all of it. Arthur did a really good job writing everything out. He really didn't want to reward hack this paper. So he tried to the principle was try to not reward hack as much as possible. But there are also other type of kind of, when we go to real sim to real, there's some augmentations like you put some perturbations so that it knows how to recover, and all of these details can be found in the supplemental, and we are also going to release the code in August. Okay, all right, so with that, we're going to train this policy that given the proprioceptive state input, output some action. Okay, and this is basically deep mimic or PHC or pulse. This reference is essentially saying that's the goal, like if that's the thing you want to imitate. And this is a blank canvas. Actually, this technically deep mimic didn't have any of these references. It was like a single policy for a single clip. And back then, it was really hard to do this goal conditioned RL. And I was like, Jason, why can't you just put this goal? And then he's like, it's too hard. And really the difference is that now there's like GPU for robot, like these things like that is much more large scale. So now people other than Jason can actually train these things. So now this is called tracking in the literature. PHC did this too. One thing that we actually had to do was to do a mocap pre-training. So there's this data set that actually have G1 in the mocap way. And we train on this first, like the goal condition deep mimic. And this is really important for us to later train it on our own data because it's a lot more noisy. But this way, the policy kind of knows what to do. Once you have this policy, you have to add the scene, which we also did in deep mimic, where you give this height map, which is 11 by 11, very simple. This is just like MLP, by the way. And now you can actually have a single policy that tracks many clips. Okay, so these are goals. Okay, but the problem is it still needs instructions. Okay, this is a really nice visualization. So before I play, the red dots are what they should do. The blue robot is the direct policy output before sending it to the PD controller. The gray robot is the actual rollout after the PD controller. Okay, so let's play this video. So you can see actually, when the robot tries to step, you see that the blue is kind of giving this really strong action. And that's because the PD controller needs to put a lot of force. So it's kind of really cool to have this visualization to see what's happening under the hood that gets converted into it. Okay, but you see the problem? The problem is that you need these red dots. And you don't know what this red dot should be if you don't really know what the environment is. So if you actually wanted to do real, you don't know what exactly this should be. So we really need to remove this this dependency on the reference joints. And so, yeah, so it needs this instruction. This is okay on a flat ground plane, actually, because then it's kind of like copy this animation and you just like play it. But with the environmental interaction, this becomes a big problem because in real, you don't really know what it's supposed to be, or you have to have known exactly what, even if you know, it's kind of annoying. And then if there's a staircase you've never seen before, you can't really do this. Okay, so what reference to use? So our solution was to let the policy figure it out. So then we have a third stage where we distill this one into a much more under-constrained policy that only takes in the root. So it will tell you, like, you have to say something to it. So be like, go forward, okay? And then it doesn't really know what exactly to do. You can do anything, just go forward and not fall. And this is the thing that we train. We call this the generalist policy. The generalist policy is trained by distillation in a supervised learning way without RL, with Dagger. So basically we have that stage 2 full tracking, and then now you reduce it to underprivileged, under-conditioned policy. Okay, so now you can actually have a joysticks or any other type of high-level controller that will tell it what to do. So in summary, this is the step, which is first you do mocap pre-training on the controller. And these are the targets, like joint targets, proprioception, height map, and the root direction. This is what it gets. You add the height map. Now you distill, you remove the joint targets with the root conditioning with Dagger. And then finally you do RL fine-tuning. And this RL fine-tuning allows you to make it more robust to do sim to real transfer. So here are some zero-shot sim to real results. Yeah. So technically, I think this staircase was seen during training in our data. I think this one, like they trained it on, like there's a video from that part of the world. But when they were really taking this robot out and walking around, they weren't really thinking about going to places where they took a video. They were really just out around all day. And you can go to our website and take input videos. I mean, it's really interesting. These small things that you don't really think it's such a big deal actually is kind of a big deal. And it is too to my baby, actually. My baby can't really, it's actually a big jump. Okay, all right. So that is Video Mimic. And there is actually lots of room for improvement. In general, I would say this sim to real to sim process is really lostful. Every single stage you're losing so much. The monocular 4D reconstruction still needs more work. The Megasum is amazing, but they can all result in slightly duplicate ghost artifacts. But this is very bad for sim. But this is also kind of thinking, I feel like the simulation should also be more robust to these things. The feet can be buried to the ground, and these methods still struggle in low texture regions. The meshing over smoothes, and you really want these high frequency motion like information in the reconstruction for like staircases. But it's really difficult to tune this because there are holes, and sometimes there's like an outlier point cloud which will make it all of these things, and so that's hard. The retargeting, it's like the contact optimization, you kind of want some flexibility. It's still kind of, there's not that flexible. The LiDAR height map is quite, low dimensional. It doesn't have RGB. The simulator is lots of problems. Like if you play around with it, there's like so many poses that you can do, and it's like that's not gonna really stand, but it's like it's okay. How are we going to incorporate dynamic scenes if we want the robot to, walk around or like sit on a chair that is moving, that kind of things. And we only learned this from 123 clips, and we really would like to scale. Like our goal was to get to 1,000, but we just like ran out of time. Yeah, so every stage, there's so much more to do. Okay, so the robot does look a little bit inebriated, but I would like to show you some exhibits, human exhibits. So this is actually the first time she took some steps. Those the first few steps. She's very excited about it. And this picture, video, is the one where she first walked outside with shoes. And this looks really very much like our Juban when it's just starting. I think Juban is slightly better. And it's really interesting because between these months, actually, she was already walking really well in the house. But when she had to wear shoes, it's kind of like sim to sim transfer, because it's like you need to figure out how that works. And so she's like doing this online learning. And the bonus, it took another 2 months for her to run down a train. Here is she running down a train. So I mean, that's actually not that long in like GPU hours, but it's still actually not significant. I mean, it takes a while. Yes. Okay, and another thing is yeah, okay, good. Okay, so last but not least, we're really into making useful tools. Of course, there is Nerf Studio, which we didn't really use in this particular one, but we could to get more colors, and Gsplat, but I really want to make a pitch for Visor. So Visor is a web-based 3D visualization that's implemented really well. It has a 3D viewport that you can move around with a really easy to configure GUI. So this was actually the underlying viewer behind Nerf Studio, but you can actually use it to view point clouds, simple body meshes. The new update is that Visor is now integrated into robotics platforms. So all of these, Pyroki is this IK solver that we wrote, also in Visor. And Isaac Gym, these are some reconstructions from our results, is in Visor now. You can actually see your, you can plot anything in this, right? So this is, you can like take your favorite plots from your training. And Arthur said that this was like groundbreaking because it's really actually hard to see what's really happening when you're training on these things because these visualization is not really there. And now this is in Mujoko. Another nice thing is now you are free from your, desktop. Like you can actually access this as a web viewer. So here are some examples when we actually first got the LiDAR map going. We're using Visor to visualize, and so it was really good tool for debugging. Another thing that I really should say is that at every stage of our policy training, we did it so that it's instantly deployable, meaning that the the inputs that it gets are the exact same thing that the robot gets in the world. Okay, So you can also use this for hosting your results, which is very cool. You can actually share any links. You can send it to your advisor. There's movable links, which is amazing. Okay, and then lastly, there's this Pyroki, which is basically PyTorch for robot kinematic optimization. This is like Simplify, but with PyTorch. It's actually trained, optimized with Levenberg Marquardt, and then has the proper Lie algebra optimization. So it just makes everything faster. Actually, I think in a lot of our optimization now we use this as a backend. So it can do a lot of collision, online planning. There's lots of great examples on the internet. It's an open source project, so we'd love to get your contributions. And this is how we did this retargeting. Okay, with that, I'd like to say big thanks to my group because this was such a big collaborative effort. And I will take any questions. Thank you.
Yeah, thank you, Anu, for that amazing talk. Do we have any questions from the audience? Yeah, feel free to walk through.
Thanks for the amazing talk, especially for middleman. Very interesting. I want to ask, have you tried for training the policy and you just do different implementation for the terrain? Like for example, you have different maps and you train the policy, and then just try it in real world, like without capturing different things from video, just do application.
Yeah, I think like Ilya has this type of directions, but they were mostly, I think, in dogs, not humanoids. I think that that's a good question, but I think the sense was that there are some of the robotics directions is going in this way, but we just didn't really think fundamentally, philosophically, that is a scalable approach because the environment has to be authored by people. So this is actually more about like a framework in which the environment can be learned from the data. And so this is why we didn't really like do this type of things. Yeah, thank you.
All right, let's thank Andrew for the amazing. Andrew will be here for the panel discussion at the end. So if you're curious, stay here until the end, and we're open for the questions for the discussion. Thank you, Andrew. So our next speaker, if you work on digital humans, is very
Want me to, now you can hear me?
Yeah.
Okay, and I'm still, but it says I'm still sharing, but you don't see it? Okay, okay, good. All right. Human Foundation Agent. This is joint work between Max Planck and Meshcapade. And, you know, I've really been inspired by what's happened over the last few years. We had in 2021, you know, foundation models for 2D image generation, then text generation, then video generation. Now we have several companies out there and also research groups working on generating 3D and talking about spatial intelligence. So it's natural to think about what comes next. What's the next paradigm? And I really think, well, it's sort of obvious, it's 4D. But what does 4D really mean? And what I think is interesting is what is embodied intelligence. And as a, you know, sort of humans are sort of the epitome of what I think of as embodied intelligence. And we'd like to be able to capture the richness of their behaviors, their interactions with the world, their interactions with each other, their ability to solve tasks and then recreate this in artificial systems. Now, for the purpose of this talk, I don't care whether that artificial system is a humanoid robot, which would be super cool, or a 3D virtual character, and we'll talk about, well, we could talk about how you render a character. I'm even agnostic to that. I don't care whether it's a game engine or a diffusion model. But what I want to do is produce intelligent behavior that looks like human behavior. And that's why I call it a human foundation agent. So it's a foundation model. So it's trained on lots of data and it should be able to generalize as foundation models do. But it should have agency. That is, it should be able to interact with humans, us, real people, or other virtual characters. And it should have some form of embodiment where those actions and behaviors are human-like. Now, there's lots of cases in the world where you want to have intelligent agents, you know, working on the internet, and they don't have to have any embodiment at all. And there's lots of things that might be embodied, but they don't have to be human-like. But I think as soon as we get to characters that are emotional and we want to engage with, virtual characters, then they need to have motions that are human-like. Even if they don't look human, the motion is really important. The timing of everything, the nuance, the little, how they interrupt and interact and so on. And if we have humanoid robots, you might say, well, Michael, they don't need to be very human-like in their behaviors. But I guarantee you, if there's two companies selling humanoid robots and one of them moves more like a human, that company is going to win, okay? Even if they can both wash your dishes, which would be great, people are going to buy the one that isn't creepy, okay? So I think we want human-like behavior. So I see four key components to solving this, creating this human foundation agent. There's a fifth one, and there's probably more, but we focus on four at the moment: perception, reasoning, behavior, and embodiment. And I'll just walk you through how I think about this. The truth of the matter is that you know, all those foundation models we've talked about that have been so successful, they've been successful for one key reason, and that's the scale of the data. And you know, it's huge amounts of text, huge amounts of images, huge amounts of video. And in these cases, data is easy to get. In the case of 3D human behavior, data is not so easy to get. You can do motion capture as much as you like, and you're never going to get to the sort of scale of which we see in these other cases. And in fact, you might think, well, and that's what we really want. My goal is to effectively capture everything that's ever been done. In effect, anything that a human has ever done, good or bad, legal, illegal, whatever, it's probably been captured on video somewhere, right? And if we can take that video and turn it into a 3D representation of detailed human movement, then we have the kind of data set we need to train the intelligent human agent or the human foundation agent. And if we have video of this, it's way better than having the best mocap in the world, because you not only have the motion of the person, you have all the scene context, you have all the richness of it, you have the audio, you have, you know, what are they doing, what's been happening in the movie or the YouTube video or whatever it is. You have all this richness, which we need to understand what people are doing and why they're doing it. It has to be contextual. So yeah, there's a few other slides I'd like to talk about, but we'll see. I might come back to them, but that's the basic thesis. And so what should this embodiment be? And I'll just talk briefly about it, because our hypothesis for many years has been it has to be some sort of 3D surface-based shape representation, because we're 3D, we contact the world not with our joints, but with the surface of our skin. We express our emotions and our behaviors through our surface, and we need to have a 3D representation. So I'm not going to tell this audience really about Simple, as you're probably familiar with it. We think about Simple as the language of human movement. It's 100 numbers, basically, and you get a simple function that gives you a function M that gives you a triangle mesh out. You give 100 numbers, theta and beta, for pose and shape. And these numbers seem to be something that large language models can reason about. So that's a win. We had a paper last year at CVPR called Chat Pose that was a first step towards having large models reason about. So I'll tell you what we're doing this year. One thing I wanted to just bring to mind, so people may be familiar with Simple already, but you know, and Simple has been popular because it's a computer graphics model, effectively. It's designed to be compatible with graphics hardware and software. But there is a little problem with it, which the Simple skeleton in this is not a human skeleton. And one of the things I really want to get to is the human and how they behave. And so I just wanted to highlight this, since this community may not be familiar with the work that appeared at SIGGRAPH Asia on building a biomechanical version of Simple. We start with the amass data set, which is a lot of mocap of simple bodies, simple X bodies. And our goal is to put a biomechanical skeleton inside these models. And so the way we do that is we take animations like this, we put virtual markers, the little green dots, and these biomechanical skeletal models are designed to be trained from mocap marker data, because everybody uses Vicon or something for this. And so we create virtual Vicon sequences and then fit the biomechanical skeleton inside the Simple model. And this is a skeleton that we designed that specifically has good shoulders and spine, and puts together several models that hadn't been put together before. And it's called Skell. It's basically Simple parameterized by a biomechanical skeleton. One advantage of this is that instead of having 72 degrees of freedom, which Simple has, it only has 46. The Simple is over-parameterized in terms of human body motion. And so it's a simpler model to work with, no pun intended. And it will get you, we're continue to improve this, by the way. This Skell doesn't have fingers and feet properly, and we're making it better and better. But you can you do all the standard tricks that you do in terms of you know, estimating it, regressing it from video sequences. If you can regress Simple, you can regress the Skell model. And if you regress Skell, then you've got access directly to the skeletal structure, biomechanical structure of the body inside. So we've been working a lot on going from the outside in. There's a little digression on the embodiment front, but I wanted people to know about Skell. So perception piece. Perception here means two different things. First of all, if we're going to have an intelligent agent or humanoid, for example, it needs to be able to reason about us in 3D. If you want your humanoid to hand you a cup of coffee in the morning, it better be able to estimate your hand motion and hand it off properly, for example. But we also need it to train such a model. So the perception piece is about understanding 3D humans and their movement, and so this is dual use in a sense, dual use in a very positive way. So the goal is video in, humans out, simple body models out. We should be able to deal with moving cameras, any camera. The humans, it could be multiple people. They should be in world coordinates. We should be able to estimate their hand motions, their facial expressions. It should be robust to occlusion, framing issues, you know, so on and so on. We'll get to more results. So the standard model that's been around since Anju did this in the CVPR 2018 is HMR. This is a classic approach. You've got some cropped image region of a person, call that eye. There's some encoder that generates some features. There's some MLP most likely that takes that and generates theta and beta, the pose and shape parameters, as well as some camera parameters here, scale, rotation, and translation. And the output then is a simple mesh, vertices. Okay, but this whole approach has got a lot of actual problems, even though just about everything in the field uses this. First of all, it focuses on a single image. That's one image I, and we really want to look at to exploit temporal information. It looks at a little crop, which makes compute easy and everything, but it ignores all the scene context and what might be happening around the person. It uses an unrealistic camera model. It assumes that the person's estimated really in the camera coordinates, not in world coordinates, and we don't have a proper camera. So I'm going to address. I mean, we worked on various pieces of this, fixing all of these little pieces. I'm going to basically work on all of them. I should have mentioned the theta and beta. That was the Skell model. That was trying to make that better also. So we've been working on that. But I want to tell you about prompt HMR, which addresses all of these different pieces, and I think is currently the state of the art. So that will be appearing tomorrow morning, and I encourage you to come by and chat with all of us about prompt HMR. So I think about this, the classic way that people, HMR is a method of going from pixels to parameters, right? You train it on crops, there's no scene context. But we want to deal with scenes like this with rich social interactions and so on, and we want to be able to capture people in 3D space interacting with each other. So how do we do that? Well, if we think about vision foundation models, they already know a lot about people and what they do. They know about their interactions with the world and with each other. They're very much, very rich. And yet these HMR style models don't have any of this semantics. They don't have any of this rich understanding. So how do we pull that in some way? How do we combine these things? So with ChatPose last year, we made an attempt at this from the direction of a foundation model, a large vision language model. But the quality of the output parameters wasn't all that good. It was okay, but it wasn't great. So now we're approaching it from the other direction. Can we take a really good HMR style model and juice it up with some information about the world? And that's in the form of what we're calling prompts here. And so there's various kinds of prompts that we think about, and you can think of more, I'm sure, and hopefully people will. The basic simple one is a box prompt that tells us that there might be a person there. But sometimes bounding boxes are not very reliable, but face detection is very reliable. It's like the most reliable thing computer vision has ever done is face detection. You can also get now very good segmentation of people. You use SAM2, you get very good segmentation. So can we use masks that we can track over time to do better? And what about even text? So if I can get text description about something what's going on in the scene, in this case, something about body shape, can I use that to do a better job of estimating the parameters? So that's what prompt HMR does. And it works with the whole image. We want to work with the whole image to take into account the scene context. So we take a whole image and then we encode that and with a richer backbone, Dino V2. And then, so that gives us an embedding of the full image space. We have an estimate of the camera. I'm not going to talk about that right now. We have an estimate of the camera. And then we have all these different prompts, which may be there or may not be there. The only one we require is the box prompt, but we're very tolerant to errors in that. And these get encoded in a variety of ways and then fed into the SimpleX decoder that decodes people in the scene properly, taking into account their interactions and so on. So these box prompts are, we trained it in such a way that they can be any size and shape. We want to make it really robust to that. So here, just varying the box size, and on the right, you see that the body shape and pose doesn't change very much. It's quite robust to this. The mask prompts help a lot in cases. Bounding boxes are terrible when people are overlapping. We get all kinds of bad results. But when we use our mask prompts, we can disambiguate this and still get good estimates of body pose and shape. And then text prompts really help. In this case, we're just using them for body shape estimation. Yellow is big error, blue is low error. A standard baseline method doesn't do so well, but if we add in information describing the body shape, we get much better results closer to the ground truth. I'm not giving you all the details. This is built on some stuff we did before on Shapey and Body Talk. So let's compare this qualitatively with some existing state-of-the-art methods. Multi-HMR, for example, is a very crowded scene. It misses several of the people and doesn't put them in a very good linear structure in the world. They're all sitting on a bench or a series of benches. Prompt HMR gets all the people and figures them out how they line up. Multi-HMR here has trouble with the crowded background, the occlusion. It puts a whole bunch of people in the foreground instead of just one person, whereas Prompt HMR figures it all out. So you can refer to the paper on the website for lots more examples. We extend it over time in a very straightforward way. We run it per frame. We get features out. We have a temporal transformer that combines those and outputs simple X at each time instant, along with contact information, foot-ground contact information. This is all still in the camera space, however. And look, this would be better to train this all together end to end, but we didn't do it that way because it's easy to train single image methods and then combine them over time. To put it in metric space, we use the approach from TRAM, which gives us structure from motion estimates, and we take it into account also the foot-ground contact, which improves things, and get a world-grounded motion out. This thing runs at 3 to 10 frames per second, sort of that sort of time frame. It's not real time, but it's not terrible. So just for comparison, GVHMR is this gravity kind of based method. So for grounded human motion, in this case of the skateboarder, it doesn't figure out that they're translating in the world coordinate system. Our method on the right-hand side, in the lower area, you see the camera being tracked. It's the little red frustrum moving through the world, and you see the trajectory of the root joint of the person as well. So we get good camera motion and the person translating in the world coordinate system. This is the German foreign minister until recently, Annalena Baerbock. She's a good trampoliner. And you see with GVHMR, it doesn't capture the vertical motion properly. It looks good in the camera coordinate system, but not in the world coordinate system, whereas Prompt HMR gets the vertical motion. And then when there's very close motion, like in something like this, if the upper row, you see that now the body is flipping all around. But when you have the mask prompts from SAM2, it's much more stable. Not perfect, but it deals with occlusion much better. Okay, table of numbers. These are classic numbers. These are not world coordinates. These are camera coordinates or Krusty's aligned versions of joint error. Prompt HMR among the full image methods is the most accurate, and among the video-based methods is, I think, currently the most accurate across multiple data sets. And then in terms of the world coordinates, oh, I don't have the world coordinates. Why do I not have the world coordinates? Well, it's even better in terms of world coordinates, but I'm missing a slide. I apologize. If you're interested in trying this commercially, there's a version of it called Mocapade 3.0 on the Meshcapade site. The difference between Mocapade and Prompt HMR is largely training data. Mocapade is trained on isn't trained on the academic data sets. It's actually the academic version may actually be more accurate. I don't know, because there's a whole lot of good academic data sets that we're not able to train on. But it works. Both of them work pretty well. So this is here. This is for Anju, I guess. Nice visualization. You can see the people in nice world coordinate system estimates of the people in this case. Okay, and what's coming next? There'll be an update of Mocapade coming with adds facial motion. So this is getting towards what I wanted to do. So robust enough that we can take video at scale, capture the full 3D body of multiple people with the hand motions, the facial expressions, the face motions, and really do motion capture at scale in the wild. That's the goal, and have enough data to actually train things. So that is Prompt HMR, and I encourage you to come talk to us about it and try it out. It's on the web. Yes, sure. Prompt HMR is trained on a mix of various things. So it's a combination of things. So the 4D humans, but our version of it, which uses camera HMR to get more accurate, it's more accurate than the original 4D humans data set. Bedlam, of course, a mix of other things. So, yeah. I could give you a Bedlam talk too. We have a new version of Bedlam coming, Bedlam 2.0. Get ready for that. It's better than Bedlam, and it has a lot of camera motions, extreme camera motions, all kinds of camera motions, more body shapes, more clothing, more motions. And if you're working on trying to estimate humans in world coordinates, you want to be using Bedlam 2 because it lets you train end to end both the camera motion and the human motion. So that's going to be the answer next time you see me, Bedlam 2. Okay, the reasoning part, so we need, we're more than simple parameters. I'm a fan of simple, of course, but we're a lot more than simple parameters. And perception is more than parameter estimation. So we really want to be able to reason about people and the behavior and what it is they're doing. And how do we leverage LLMs to help us with this? I mentioned chat posts from last year. So this year we have something called Chat Human tomorrow morning also. And I encourage you to come by and chat with us there. The point of Chat Human is that the computer vision community has developed all kinds of specialized tools that are really good at estimating human motion, generating human motion, like in the middle here, estimating contacts on the body, tracking faces, estimating facial expressions. Like we've got tools, right? And we've got a ton of them. And each of these tools excels at what it does, but they don't benefit from the expertise of the others. And if you want to use them, how do you put them all together? It's confusing. So what do people do? They've got the human's got a problem. They've got some task. They got a bunch of tools. They say, well, which tool should I use to solve my task, right? And then use my tools. I get some outputs from my tools. I ask myself, like, is it reasonable, ballpark? Is it pretty good? If I've tried multiple tools, is one of them better than the other? Can I combine information from different tools to really solve my task? What about if I, have the output of a tool and I use my own knowledge about the world can I do better? And so that's kind of what humans will do before they generate a response. So we wanted to mimic that. We wanted to train an LLM to use tools from the vision community. And so crazy idea is to let them read the papers. Like, how do they figure out how to use the tools? Well, it turns out that academic papers contain enough information to really help you figure that out. Congratulations to all of you for writing good papers that are clear enough for LLMs to understand. And so I'll tell you a little bit about how we leverage papers. But the basic pipeline is as follows. The input could be text, images, or vector input, like simple parameters or things like that, or combinations of these with some task. And we have a retrieval augmented generation style model, which takes some tool documents, which are generated from these papers, and tries to reason about which tools are the appropriate ones to use for a given task, formulates how to call that tool, uses those tools to generate some outputs, which could be text, or it could be images, or it could be vector information again. The LLM reasons about these, tries to figure out how to formulate its response, and then responds in the form again of text or images or simple models or something like that. Okay. And Chat Human uses 26 different tools from the vision community, the sort of vision perception tools, reasoning tools, generation tools. And to train it, you need some data, of course. And so, we use these information we use GPT-4 to generate training data. And the supplemental material of this paper is significantly longer than the paper itself, because it goes into great detail about how you generate training data for this problem. And I'm not going to go into it, but in addition to creating the tool documents with GPT-4, we also generate instruction following data for training using various data sets where we have ground truth, 3D human pose, or text labels, or so on. And so we train the model to solve these various tasks. When it when it uses the tools, it has various kinds of situations it might be in. It might just need a single tool, or it might need a chain of tools that it has to use, or it might need to do a bunch of different things and then combine them. And so it has to first reason about how it's going to solve the task, and it can either use one of several different strategies. Once it's done, use the tool. So here it's given an image, and the task is to estimate the BMI, or body mass index, of this person. It doesn't have a tool specifically for body mass index, but it's an LLM, so it knows that body mass index is a function of height and weight. So it calls a tool that gets it the height and weight, and then it gives you back the BMI. That's a pretty simple task. It has multiple methods for estimating human pose and shape. And so when you ask it to, here's a pretty challenging yoga pose. You can probably barely see it, but it's a challenging yoga pose. And it runs several different methods. And then it's been trained to evaluate different things. And so it takes these results as images and then asks itself which one is more accurate, which one better reflects the pose in the image, and then gives you the result back of the better one. And now this is a way that the method can actually be more accurate than any of the individual methods that it's using. If it's good at judging what a good outcome is, then it can be more accurate. And it can also do things like, give me the pose of the person who's frowning, right? So, again, it's using its general purpose knowledge here, right? And this one I like. I want my cooking robot to mimic my hand motion, the hand motion of this individual. Please estimate the hand pose. And so, of course, it can do that pretty well. And then you could ask it, what's the person doing? And of course, LLMs tell you a whole lot of stuff, and they'll tell you that maybe looks like he's stirring a pot, he's doing some cooking, and he's maybe going to season the dish. And you could say, well, give me the motion, generate the motion for his next action. And it understands how to generate human motion based on stirring, for example, and would give you back some generated human motion, for example. So that is a quick survey of Chat Human. Again, come see us tomorrow. In terms of the last piece of this was the behavior piece. And I'm not really going to have time to talk about that because I'm out of time. But our goal is to generate virtual humans that move like real humans. They move in real time. They're always on. They feel alive. They're aware of the environment and react to it. They're controllable. They have goals. So they can do semantic tasks. They can understand us, talk to us. They have personality and so on. And our vision is that by mining the internet for all of human movement, we'll create a generative model of human behavior and use this to animate both virtual humans and to train humanoids. So I encourage you to come to the Meshkate booth, booth 1333, and you can try out this demo. It's our Mogen product, and it is a virtual character that is trained purely from data. There's no physics training, no RL, no nothing here. It's all data from a mass, and you can interact with it. You can poke it a lot. You can drag it. You can do things, and it always reacts like in kind of a realistic way. I like this because it's effectively a learned low-level motor control system for humanoids, and on top of that, you can then learn other kinds of behaviors very, very rapidly and efficiently. So come ask us. Jan here's in the front row. We'll be at the booth, and you can come ask him about this. So that's my quick tour of how we're getting to the Human Foundation Agent. There's a lot more to say, so come and ask. But thank you for your attention.
Thanks, Mike. That's Paul. Do we have we can take one question from the audience now. Okay, I can ask one.
Oh, there's a hand there.
Yeah, awesome.
There's a hand right here.
Can you come to the mic?
No, it's you. You have your hand up. Yep. I mean, your hand wasn't very high, but I saw it, so it's. Yeah. Yeah. Thanks.
And I saw it had understanding about the motion prediction, reconstruction, and generation. And I'm wondering if it can understanding the semantic meaning of the human motion. Like if I do this close, it maybe means goodbye or hello or things like that.
Yeah.
Is is a work kind of like things?
Yeah, it's a really good question. So we don't have specific training data for that. We train on things like on poses. We have text description of poses. I'm not sure that we have text description of motions, and I'm not sure that it will generalize on its own to figure that out. It's a good question. If Yao is in the room, she might. Oh, no. What do you think, Yao? Thumbs up, thumbs down. Easy to add. So the answer is, if you have data, training data, it's easy to add.
The Gemini is kind of action to generalize to new tools. For example, if you already have a specific model that can understand motion, can give you motion descriptions, given the sequence, motion sequence, and then you can just add it into the agent system, and then it could have the tools, have the function of the tools to be provided. Without training, without additional training, you can do this. And if you have extra data added for the training, then it will be better. And it should be.
All right. So the answer is, it's a platform in a sense where you can keep incorporating new things. And then, yeah.
All right, let's
All right.
thank Michael again. Our next
Okay, and I should share the screen. So here, share. Can you check that it's all fine? Yeah, okay. Good. All right. Yeah, thank you very much for the introduction. Unfortunately, I'm not as democratic as Michael, so I already prepared one talk, so you have no choice, sorry. Yeah, so today I want to talk not so much about human object interaction. This is what I talked earlier this morning. I want to talk more about how to learn a large-scale 3 human and object reconstruction model. And to solve this problem, I think we have to solve many challenges, and I'm going to focus on 3 challenges that I think are important. One is how to extract 3 information from existing image-based foundation models. Second is we have to train models that are flexible in terms of the inputs and outputs. And finally, I'm going to emphasize how we can use synthetic data to break the barrier of lack of data. All right, so let me start with Human 3D Fusion, which is work that we presented at NeurIPS last year. And this is work by mostly Yushu and Xue, who's a PhD student in my group. So here we address a classical computer vision problem, which is going from a single image to a 3D avatar, like a 3D reconstruction, which should contain the geometry and also the appearance. And how many of you have worked on monocular human reconstruction? Can you raise your hand? All right, so I don't need to convince this audience that this is a really hard problem. You don't see the back of the person. You have to deal with scale ambiguity, depth ambiguity. And basically, we are now able to reconstruct models that start to resemble the quality of 3D scans. So basically, this is the input on the left and the reconstruction on the right. The output is basically a Gaussian splat representation of the image that you're seeing. And the nice thing is that we can reconstruct the front part and also the back part of the human. And we're not restricted by the simple geometry, but we can reconstruct, for example, like this bride that contains like, flowers and is holding objects. So as I was saying, like, I don't need to convince you that this is a hard problem because of like wide variety of body shapes, texture, clothing, accessories, and so on. And, up until now, we didn't have so much data to deal with all this variety. But we have these cool image foundation models that can generate really beautiful images of people, right? But they are not in 3D. And so what some researchers said is like, okay, we can adapt, we can fine tune these image purpose models to generate multiple views of one view. So you can give like an image like XC, and then you denoise like multiple views, generating multiple views of the person. And this is like some sort of 3D representation in some sense, right? Because you have multiple views. Now, the problem is that these views look good, visually appealing, but if you attempt to reconstruct these views, you get something like ghosting. For example, like on the feeds, like you had like multiple feeds and you get blurry results from the triangulation. And this is because it's very difficult for a network to produce like pixel aligned, like multiple images that satisfy the rules of multiple view geometry. So how can we solve this problem? Well, some researchers said, let's take the multi-view images and train on top of these sparse 3D reconstruction to produce a NeRF or an SDF or a Gaussian splatted representation. Yeah. Now it turns out that this is good, but it's not good enough. Like you have like avatars that look fine, but you have like these ghosting artifacts. And our hypothesis is that because this happens because we're trying to fix errors instead of trying to prevent them. So we're trying to take multi-view images that are already multi-view inconsistent and then reconstruct a model. And this is already too late in the pipeline. So we argue that we should address the problem earlier. So if we look at diffusion, just to refresh what the diffusion denoising process does, you start with XT, which is a noisy signal, and you take a series of steps to get the ground truth signal X0. Now, each of these balls here, these blue dots, is like a sample. In this case, it's a multi-view sample, right? A multi-view representation of the input image that you have given. Now, the problem is that at every step, this is multi-view inconsistent. So at the end, you get a multi-view inconsistent result. But we know there's a manifold of ground truth multi-view images. Those are the ones that come from renderings of a real 3D object. So the idea is at every step of the denoising process, we want to project to this manifold such that we keep correcting these errors during the diffusion in the denoising process. So we do this in the reverse sampling strategy. So at a high level, what we're doing is we're taking a 3D Gaussian splat reconstruction model and a 2D multi-view diffusion model, and these two talk to each other, and they are synchronized at each step of the denoising process. So the 2D multi-view diffusion provides a very strong prior for the 3D GS reconstructor, and the 3D GS provides this multi-view consistency of, it makes the multi-view diffusion model satisfy the rules of multiple view geometry. All right, so a little bit more in detail for those of you that are more interested in the technical details. How this works is as follows. You start with the noise and you denoise and you want to obtain the signal, in this case, the Gaussian splat representation. Now, in a usual diffusion process, when you denoise, you basically remove noise from the image and that's it. But here you do something more involved. At every denoising step, you have to obtain a 3D reconstruction. So what we do is we take these noisy images and the conditional signal, we send it to multi-view diffusion, which at this point might produce something that is still multi-view inconsistent, but it provides a strong prior for the 3D generative model. Now the 3D generative model will produce the Gaussian splats that we can then render into the images, and then basically we can backpropagate to satisfy a rendering loss through the 3D generative model and the 2D multi-view diffusion. So at the end, we are training the model to minimize a rendering loss, but at every step, we're lifting to 3D, rendering, and back projecting and then backpropagating the gradients. And by doing this, we're at every step like fixing errors. And this leads to results that are much more multi-view consistent. And what is cool is because we have this 2D multi-view diffusion model, like we can leverage the knowledge from this foundation model and we can generalize to, for example, like this woman wearing kimonos, or like this guy that is wearing some sort of rock. And actually I didn't mention, but we fine-tuned this model on 3D scan data, and none of these clothing nor objects were seen in the data. Of course, one might ask, like, how does it compare to more simple motivated models? And you can see that things like, for example, like a bride with this bride dress, like it will never work with simple because simple cannot deal with this type of clothing. You can use a model like Icon or Econ, which is specialized for having clothing and has like simple under the hood, but still struggles to reconstruct this. And this is an example that I really like. This girl is holding this board, and the model can reconstruct the arms at the other side of the board, which means that the model really reasons about, you know, what's happening. Like it understands that the girl is actually holding the board. And actually, this method is not specific to humans. It can reconstruct general objects like this Ninja Turtle here. And because there's nothing specific to humans, we generalize this model to objects now. And this is what you can find in a recent paper that we call Gene 3D Fusion. This is a journal version of the human 3D fusion. And so, for example, we can reconstruct the shoe. And when we compare to video diffusion models, we see that we obtain like nicer, like multi-view consistency. Now, SV3D, for example, is a very strong model, but it's still hard to get like a very continuous video of this multi-view rendering. You can also reconstruct animals like this lion here. And again, this is a general purpose model. It's not trained for animals, it's trained for all sorts of objects and humans. And what was cool is that, and this really impressed me, like that it can reconstruct two people when we never specifically trained for two people. Here's like, for example, this mom holding a baby. This is like kind of a failure mode because like the baby geometry is a bit flattened. So it's not perfect, but it's getting pretty good. Here's some more examples of different objects that we can reconstruct. All right. Some of you might say, well, but the details are not quite right. Like this doesn't look like the quality of a 3D scan. And we have a new version. This is still not, it's still under review, but these are avatars completely generated from scratch, no scanner. And you might recognize Joker here, Obama, and Einstein. And you can look at the geometry. This is like the avatars with texture. And this is like the geometry. And so, I mean, this is convincing, you know, a couple of years ago, I was planning to have some budget to buy a 3D scanner, and I wasn't sure. I asked people in my group and they said like, oh, we're not so sure. Now I'm convinced we don't need a 3D scanner anymore. Like these foundation models, they have so much information that soon we'll have like 3D scan quality avatars. So I'm going to spend the money maybe in robots or whatever. All right, so the foundation models have information. If you're interested in knowing which foundation models are good for 3D reconstruction, I invite you to come to our poster session, like it's called Fit to GS, probing visual foundation models with Gaussian splatting. And here we evaluate, basically we train a Gaussian splat reconstructor, and then we evaluate which of these models, like Dino, Radio, Meta, Sclip, and so on, is good for the task of 3D reconstruction. And we compare like each of these methods against like geometry quality and appearance quality. All right. This concludes the part of like how to leverage these image foundation models. Now I'm going to emphasize how to train models that are flexible in terms of the inputs and the outputs. And this is the work neural localizer fields. Like this is for 3D human pose and shape estimation. And this is work led by Ishvan Sarandi, who is a postdoc in my group. Right, so we've seen an explosive growth of data sets available. That's great. It's good news. And the goal of training is to leverage these heterogeneous data sets for high accuracy. And the goal at inference is to have the flexibility to choose the output. So when we look at the data sets, and this is just a snapshot, there's many more. I'm sure I'm missing some. It's really great. We have a lot of data. But when we look at the annotations, we have like a zoo of possible annotations. Some people use simple, some other people use simple X or COCO joints or human 3.6M skeleton. Some people like to annotate a lot of joints on the face. And so it's quite varied, the amount of annotation that you can have. And the typical approach is to convert everything to simple, for example, and then basically train from that. But this conversion is ill-posed and it's tedious. So we don't want to do this. So our idea is to turn the human pose estimation problem into a continuous point localization problem. So we want to choose any point on the volume of the human and have a network predict this point for us. That's the key idea. Right, so basically that would be the input image, and the output of the network would be each of these 3D points that the user selects. So what we've learned over the years for human pose estimation, a pipeline that works well is like you use a vision backbone, you extract feature maps, you have like this convolutional layer, you extract this heat map logits, and then you do softmax to localize the point in this volume of like features, or maybe like in 2D if you're doing 2D pose estimation. We know this works well. This is the basic version of like OpenPose, for example. And now the question is like, well, we have to fix the skeleton. We have to choose, do we predict these 14 joints or 20 joints and so on? So if we want to go from 14 joints to 28 joints, now the question is like, what do we need to do in this architecture? In particular, we have heads here. So if we have 14 heads for 14 joints, if I want to now predict 28, how many heads will I need? Anyone? It's not a tricky question. Well, you will need 28 heads. And if you want to predict like 100 joints or maybe like 1,000, you will need 1,000 heads that will not really talk to each other. So it's not really optimal. So what we want to do is like, instead of having a pre-decided set of joints to predict, right, with separate weights, we want to have a localizer field. So now we're going to have a network that we send the point to the network P, and this network will predict weights that will be convolved against the feature maps in order to localize this point that we have chosen. And why this is so cool, in my opinion, is that now we're not committed to one skeleton. We can predict any skeleton because like we choose which points we want to predict. And so to give you a demo of this, and a colleague of mine told me that this looks like a colonoscopy, and you will see why. Like the user selects like which point on the body you want to predict. And on the right, you see the network predicting these points for the different people and also over the video. And because we were able to consume a lot of data, we could get like really good results. Like, this is, you might ask, well, if you predict points, like what if I want the simple model? Well, you can do inverse kinematics very fast. Like we have the code for, if you ever want to go from points to simple parameters, you can use this code. It's much faster than what's available. It's not very complicated. I will not explain the details, but the basic idea is to divide into parts and do procrastes per part, and then it's very fast. But that's not the point of the paper. And because we could train from a lot of data sets, then we achieve a state-of-the-art performance. Now, in this case, where two consecutive speakers say that they have the state-of-the-art. I mean, at least like at the time of publication was state-of-the-art, and I've seen these like work really, really robustly for a wide variety of motions and interactions. And what is cool is like, compared to predicting simple parameters, because we predict the points, like this snaps better to the silhouette and predicts the body shape better. And I think it's just because of this architecture that predicts points. By the way, like Istvan just adapted this to predict also the simple, like, or the points in global camera coordinates using an external SLAM method. And this is also integrated in the code. So if you want absolute pose and shape, you can use the code. All right. So we have like, I present another method that is flexible in terms of inputs and outputs, And I think like these models, as they become larger, I think this is very, very important. I mean, like, I really like this last work. I didn't know like this last work that Michael presented on what was this foundation model? Like this flexibility to be able to ask the model, hey, I want the hands, or I want the face, I want the body. I think this is going to be more and more important. We should not train models to just go from X to Y. All right. So now I want to talk about like human object interaction. And this is work by Ilya Petrov, who is a PhD student in my group. And this is called like 3D. And it's trilateral diffusion of 3 humans, objects, and interactions. And this is work that is still not published. And so when I think of like interactions and humans and objects, like there's 3 variables that are at play, like the humans, the objects, and the interaction. Interaction like in terms of the contact or in terms of text describing what's actually happening. And this is the joint distribution, and I would like to sample from this joint distribution or any of the potential conditionals that arise from it without having to train a new model for it. So we can sample from this joint distribution, for example, sample humans and objects. Or I would also like to, for example, condition on the object in blue here and produce poses that are coherent with this object. Or maybe I want to condition on the human and the object and produce the contact. Or maybe I want to like condition on the human and produce objects that are coherent with this human, right? And I want to have this flexibility, and I don't want to train a single model for each of these modes. I want to have everything baked into one model. And diffusion is really cool for this. Like it's, you can basically, at a very high level, what you can do is at test time, if I want to predict the human, for example, I can provide noise to the model and ask the model to denoise. If I want to condition on something, I can provide the, for example, the object, I can provide the object parameters, and this will be the conditioning signal. And I imagine like these switches where I switch from noise to actual ground truth signal at test time in order to choose whether I'm conditioning on the variable or I'm predicting samples from that variable. In terms of contact, we represent it with text and contact maps, like on the body together, and we have a joint embedding so that we thought it's easier for users to specify with text than specifying the actual contact maps. And here's some examples. For example, here we condition on the chair and we can generate different poses for that chair. Or you can do the opposite. You can condition on the human and produce different human object poses for this human. And what we found out is that some poses are very informative about the object and some poses are not, right? So sometimes you have a lot of the sparse, how do you say this? Like a lot of sparse samples, sometimes like very condensed. And what we can do is like we can do it at keyframes and then interpolate in between in order to produce an animation, because this is a single frame method. We can basically know here what the object pose should be based on the human motion. Yeah, this doesn't use any physics, but it's basically learned from the data. Other things that we can do is we can take the work from Tripathi and take the image, predict the contact map and the human pose, and we can ask the model what is an object that fits this pose and contact map. And for example, here it can predict that there should be a backpack here, or there should be a chair and a keyboard. So this shows like some use case of this. All right. I want to show another example of like models that are flexible in terms of inputs and outputs. This is Unimotion. This is work by Chuchao Li, who is supervised by me and Andreas Geiger. So this is unifying through human motion, synthesis, and understanding. And so what we want to do here is like what a lot of other people are doing, like give a text, person walks forward and picks something up. But the difference is that we want to have sequence alignment between the poses and the activities. So for example, like this, the model natively produces the poses together with the text aligned in time, such that, for example, if I want to say, I want to change walk forward by run forward, I can change and I can leave the rest of the sequence intact. So I can change only specific regions. And I think this is important. Like we're seeing like a lot of interest in merging virtual human work with robotics. Well, if I want to transfer to robots and I want to know when contacts actually happen, it's important to know when things are happening, not only where. So we can do, for example, like text to motion. We can do unconditional generation, or we can do motion to text, all in the same model. For example, like we can say a person paces back and forth in a small space, and the model will automatically produce the poses that are aligned with these textual descriptions. Technically, what this means is like you have tokens for the sequence level text and the poses, and you denoise together, right? We're not doing something super fancy, but this is showing the flexibility. You can also provide noise to the model, and it will produce the poses and the text together from just noise, or we can use it to label motion capture data. We can provide poses, and then the model will basically label this for us. Right. I think I'm running a bit out of time, so or I still have 7 minutes, no? Yeah, okay, so I will just speed up and then okay, I just want to like give you the gist of how we can use synthetic data, or how we can leverage the data sets that are already available for human object interaction. So here we want to reconstruct human and object from a single image. And the problem with this is that we'll skip this because you're already very familiar with the challenges. We have data sets like behave or intercap of interaction. Now there's more, but still the scale is still very small, right? We have 7 humans or 10 humans, whereas the scale of other data sets like Bedlam or Observers, like we're talking about 10 million examples for objects. And so what we did here is like procedurally combine these data sets. We basically mix up human data sets and object data sets and interaction data sets to produce potentially millions of examples. I'm going to skip this. So if you're interested in human object interaction, you might check out this data set, which is called Procigen, which has like 1 million interaction poses of humans and objects. And now we also have it for video. And because I don't want to, I have 24 minutes here and I want to have, so what's your clock saying? I have here 24 minutes. Yeah, it's fine. Okay. It will not take much more time. So yeah, so we can reconstruct the human and the object without making any knowledge of the template. So basically this is like object shapes that the model automatically reconstructs. And then we extended this to the temporal dimension. This is called like the work Intertract. This is work by Xianghui Xie, by the way. And the thing in the middle is like the work that I presented before, and this is the CVPR result, and which notice that the point cloud is like jittering a lot, and the shape of the object is also not very stable. It's because we don't have temporal correspondence. And in this new work that we presented 3B this year, we have temporal correspondence for the object and for the human. And so basically for this, we needed to extend the data set to have dynamics. And basically in a nutshell, what we're doing is like training an autoencoder that aligns the point clouds to a common reference and optimize the object shape such that it's maximally consistent to each of the frames. And the result is like a model that can reconstruct the human shape and the object from videos. Right. And of course, like this is humans and objects, but ideally we want to have a holistic model that reconstructs like humans and scenes. And that's something that we're also working on. This is also work that is still not published, but we can reconstruct the 3D scene geometry and the object. You might recognize this person. And so we have a model now that can reconstruct the 3D scene geometry together with the body shape. And now I come to conclusion. So how to train large-scale human foundation models. I've touched on 3 topics. There's many more. Michael was pointing at other directions. Basically, one is that we can exploit the knowledge from image foundation models. And for this, I presented Human 3D Fusion and Gen 3 Fusion. I didn't talk about this, but foundation model features, they have strong 3D knowledge, and in feature to Gaussian splat, like we probe and compare foundation models, and the data sets are increasing, the formats are increasing, the amount of body models are increasing, and so neural localizer fields is one way of absorbing all this data. I've shown like 3D, which can deal with humans and objects, and in any direction. And finally, I want to thank my team of students who are really doing all this work, and it's really a pleasure to work with them every day and learn new things. And now I give you the QR code for the page where we have all the software and data, and I'll be happy to take questions now. Thank you.
Thank you, Gerard, for a fantastic talk. Now we have time for questions. Do we have a question from the audience? Yeah, I can kick it off. So I have a question about your first work, where I'm really impressed by the high quality reconstruction of humans. Do you think it's a promising direction to like combine that with the physics-based simulation of clothing? Because those are static measures, right?
Yeah.
We bring them into animation, into novel poses or challenging motion.
Yes, absolutely. I think this is a very, so what I'm starting to get a feeling that what works really well is like to like take these foundation models, which are very strong, and then you fine tune them on a bit of data that is of your interest. And then you get something that is really cool because it adapts to your new data while still generalizing like before. So maybe what you could do is take, I don't know, like Bedlam or some data set where it has like these physics simulations, and then fine tune a model and maybe get the realism from the video foundation model while like, you know, having the control of a physics simulation, for example, right?
Do you think like we need to incorporate the physics simulator into this animation pipeline, or we can have this neural network that just kind of learns a regressor from pose or motion to the clothing stage?
Yeah, I mean, the more elegant approach is to include the physics simulator in the architecture. The easier approach is to have like a data-driven model that goes from pose to the clothing. So it depends. Probably, I mean, it depends on what. If you ask me, you need something working in the next few months, I would go for the data-driven. If like, but maybe the other one is a more interesting research direction. Yeah.
All right. Yeah. Let's. Yeah.
Thank you for the great talk. I have a question about NLF. Do you think the current model of formulation fully leverage all the data that it observes, or there's still space that maybe like to 50% of the data and the model is saturated, and because the amount of data is very large?
Yeah, we did. So Istvan did a bit of analysis on it. It's very difficult to know which data sets are key, right? Because we can, from academia, we cannot afford to have ablation studies of training with, you know, subsets and so on. But what I can say is that what I think like the model leverages is that, you know, predicting this point and this point is a very similar task. So through this neural localizer field, because the weights are shared, because, you know, the points don't change so much, every time you see this point, you're having information about this other point. So I think in that sense, the data is really well exploited. It's not like, you know, independent point predictions because of this like neural localizer field that basically ties the weights together.
Like what's your gut feeling about whether, you know, how much data is fully exploited?
I can tell you one thing. So Istvan had a very interesting experiment, which he observed that this neural network was this is convolutional, but when he changed to transformers, the network was starting to learn when the data comes from a 2D data set and when the data has 3D annotation. And so it was cheating. And it was basically saying, oh, if I have 2D annotation, I will do worse at 3D. If it's like coming from data set that has 3D annotation, like I will do better at 3D. And so, you know, how we solve this problem is like Istvan had a very creative idea. He put a QR code, like a little QR code, so that it would be like it would be very obvious whether it's 2D or 3D. And then the model doesn't have this incentive to cheat. Yeah. So you have to be very careful. Like these models learn a lot of things that are not interesting, or like that's not what you want them to learn.
All right, let's thank Gerard for the amazing talk again. Now, two things. First, we have a break. Don't forget your souvenir. We have a bunch of them here, so just come over to pick it up. And we're gonna have a poster session, X called D. So that's where all